When an object moves, it's displaced to a new position, right? But look, this circular motion just keeps revolving in the same area. So asking about its displacement or change in position doesn't really make sense, right? So keep in mind that for this motion, problems ask about the time period and the number of rotations, okay? I'll help you understand this better as we solve some problems. Hello, let's study physics for 1 hour a day. This is Minsikham from Minsikham Academy. Today is the second lecture on two-dimensional motion. For 2D motion, you just need to remember projectile and circular motion, since those are the only two types you'll encounter. For projectile motion, remember our strategy, decompose it into x and y components, and analyze their graphs simultaneously. Now, what's the strategy for circular motion? The solution method for circular motion is the same as what we learned in the previous lecture. While it's the same, you need to know the notations and units necessary for circular motion. I'll write it down here first. There's something called linear motion, the kind we've been doing so far, linear motion. It's also called translational motion, which refers to movement along a straight path. Movement along the x-axis or y-axis is called linear motion because the object travels in a straight line. Projectile motion is also a type of linear motion, as it combines movement along the x and y axes. The second type of motion is circular motion. So there are two types of motion: linear motion, also known as translational motion, and circular motion. These two are a bit different. The reason is that circular motion is a motion that goes around like this. It's easy to imagine swinging a ball on a string around in circles. So circular motion is the motion that maintains a distance r between an arbitrary center and the outside while revolving. As you can see, the forms are a bit different. Linear motion moves back and forth to a certain position, but circular motion revolves around a central point continuously, completing several rotations. This is precisely why these new terms and notations are introduced. For linear motion, as you should already know, acceleration is represented by the symbol a, and what's its unit? It's meters per second squared. Does that make sense? Then in the corresponding circular motion, we refer to it as alpha, and this is angular acceleration. I'll write it down here for you. So what's acceleration alpha? Angular acceleration. So the unit here is radians per second squared, where rad stands for radian. We use the symbol theta for the angle, and its unit is the radian. Got it? For example, you know what 360 degrees is, right? In radians, we would express that very same angle as 2 pi. The unit to change the angle like this is called radian. You need to know how to convert degrees to radians. We will use it as the unit of this angle, theta, that we use. If theta is, say, 320 degrees, you can convert this to radians, right? Since 360 degrees is 2 pi, 1 degree is 2 pi divided by 360, and when you reduce the fraction, you get the result like this. So you need to convert these angles to radians so they can be used in multiplication or other calculations later, right? Therefore, I'll assume you know how to convert them to radians and move on. You need to know that the unit is called radian. Next, velocity is what we refer to as v. We were using this as meters per second, right? So in circular motion, we use omega. Omega is angular velocity. It represents the angle that an object sweeps through in a certain period of time. Therefore, the angular velocity is theta divided by time, where theta represents the angle. So velocity v is what physical quantity divided by time. It's distance, right? Represented by the variable s. Make sense? Here it's the same logic. It's velocity over time, right? That's why the unit is meters per second squared. But here it's angle per time, not distance. That's why it's called angular velocity. But originally, this was also linear velocity. Why don't we always call it linear velocity? The simple reason is that in physics, linear motion is the most fundamental type of motion we learn about first. Because it's the default and most common case, it gets the simplest term, just velocity. You can think of it as a kind of shorthand. The word linear is already implied, so we don't need to add it every time. We only add that extra descriptive word when we need to distinguish it from a completely different type of motion. For example, the circular motion we are learning about now is exactly such a case. Here we use the term angular velocity to describe how quickly an object's angle changes with respect to the center. So we use linear velocity and angular velocity to avoid confusion between moving in a straight line and moving in a circle. So how can we apply this concept in real life? For instance, in a general situation that isn't circular motion, if someone asks, "What's the velocity of that car?" we naturally understand that they are asking for its linear velocity. However, as we've just learned, if an object is in circular motion, you must ask specifically, what is that object's angular velocity, to properly understand its motion. This is why we attach the word angular to angular velocity. Because when it is in circular motion, you need to ask about the physical quantities according to the type of motion. So you don't just ask, what's the velocity in circular motion? To summarize, because linear velocity is the default concept of velocity in the most general case, we omit the word linear. So just saying velocity refers to linear velocity. For other types, you have to add a descriptor. For example, angular velocity means angle per time. Linear velocity is distance divided by time. Got it? This isn't a formula to memorize, it's just common sense. Naturally, angular velocity is angle over time, not distance. This isn't something to memorize either. Who would memorize that velocity is distance over time? Right, it's common knowledge, so you need to know this. If someone asks Minsikham, you don't memorize formulas, right? Things like velocity equals distance over time are common sense. It doesn't make sense to say you won't memorize this, right? Even if you ask someone around you who doesn't study physics, they'll probably tell you that speed is distance over time. Similarly, since we use the term angular velocity, you should understand it as angle over time, not distance over time. You don't need to memorize this, right? Instead of just memorizing, take a moment to truly understand it. So what's the unit for this? It becomes radians per second. So these two are the same concept. Then the last one. Now you just need to learn one more. The last one is distance. It's s. The unit is meters, right? Now, the part that I explained earlier here is notation. Then here is the unit. You must definitely remember the notation and units well. What is this here? Notation. This is the unit here. Use notation for formulas, but in answers, always include the units. Okay, for linear motion, it's distance, so what's the equivalent for circular motion? It's the angle, and the unit is the radian. We just call it rad for short. Radian is the unit for angle, okay? Actually, this unit becomes a dimensionless quantity by dividing length by length. We'll elaborate on this a bit more next time. For the circular motion problem, I think it's enough to understand it this way and move on. The difference between linear and circular motion is that the nature of the movement is different, and thus the notation has changed. That's why new notations and units were created for it. Don't overcomplicate this. Just accept it as it is, okay? It's simple, right? Of course, you have to memorize this. But there's one more thing. How did we solve linear motion problems? We drew graphs, right? AT, VT, ST like this, right? So how do we solve circular motion? The method is the same. We draw a graph. I said in the previous video that we would solve all motion problems with one method, right? For circular motion, we need to draw the following graphs: alpha t, omega t, and theta t. Makes sense. The drawing method is the same. If acceleration is a constant, 0th order, then velocity is linear, 1st order, and displacement is quadratic, 2nd order, okay? But that would be too simple. If that were all, professors would have no reason to test you on circular motion. So there's an extra element here, something more. There's more to it. What was the additional concept when moving from 1D motion to 2D motion? We had to account for both the x-axis and y-axis, right? Other than that, the method of solving was the same, wasn't it? Similarly, for circular motion, the graphing method is the same, but with an added challenge. You'll be asked for the period and also the number of rotations, so you'll need to find both the period and the number of rotations. They will definitely ask for the period and the number of rotations. You must study this part. Linear motion is when an object moves to a certain position, but circular motion is a motion that keeps rotating while maintaining a constant arbitrary distance. So, asking about a change in position doesn't make much sense for circular motion, right? That's why they ask for the period. The period is the time it takes to complete one full rotation, as you know. By convention, the period is denoted by a capital T. Now, what about the number of rotations? For the number of rotations, we convert theta to radians and then calculate the area on the omega t graph, right? So when you calculate this area, you get delta theta, right? For example, if delta theta is 10 pi, how many rotations is that? 2 pi is 1 rotation, so how many rotations is this? It is 5 rotations. In the problems, it will likely ask, how many rotations did this object make? Like this, right? Then you can just write something like 5 revolutions. Okay? Revolution. You've probably heard of the unit RPM, right? The R stands for revolutions and the PM for per minute, so RPM simply means revolutions per minute. Got it? How many rotations in 1 minute? This is what RPM is, okay? So why ask about rotations? Because in linear motion we track position in meters, but here the object just keeps rotating. So you'll also be asked additional questions like, how many rotations? By dividing by 2 pi, and what's the period, the time for one turn? So remember that you'll be asked for the period and the number of rotations. I'll help you understand better as we solve the problem. Okay, I'll explain this a little more here. In the angular velocity formula, omega equals theta divided by t, when time t is the period t, the angle theta for one rotation is 2 pi. That's how the formula becomes this. Make sense? Let's try to understand this more as we go through the problem. Since this is your first time learning about circular motion, it might take some time to get used to it. So please memorize the notations and units. The method of solving is the same as linear motion. Now let's move on to the next page. Uniform circular motion and uniformly accelerated circular motion. So what is uniform circular motion? In any circular motion, there's the velocity at which the object rotates, right? In uniform circular motion, this velocity, which we call angular velocity omega, is constant. I'll write it here. In uniform circular motion, the angular velocity omega is constant. So, how do we solve this? In uniform circular motion, the angular velocity is constant, so there's no angular acceleration, right? How are the graphs of alpha t, omega t, and theta t drawn? This refers to problems where the angular acceleration is necessarily 0. Then, since omega is constant, the omega t graph becomes a constant function, and the theta t graph becomes a first-order function. So this area is delta theta, right? Then this height is delta theta, right? And that's really all there is to it. In circular motion problems, the probability of uniform circular motion showing up is almost 90%. Next up, what is uniformly accelerated circular motion? It's the second type we'll cover. The angular velocity is gradually increasing, meaning there is angular acceleration. With angular acceleration alpha, the angular velocity omega changes over time, so you solve uniform circular motion like this. Since it's constant acceleration, alpha is constant. Then omega becomes a linear first-order function, and theta becomes a quadratic second-order function. Then what about this area? This area becomes delta omega, and this height is delta omega. And what does this area represent? It represents delta theta, so this height is also delta theta. This is the same as uniformly accelerated linear motion, and uniform circular motion is the same as uniform linear motion, got it? The method of solving is still the same, so what's the extra element here? If they ask for the period here, you just need to answer, and for the number of rotations, if they ask how many rotations were made, then you just give the answer, okay? Solving the problem is easy, right? These are the only new elements. As you solve the problems, it would be good to keep understanding. So let's try solving an example problem. A small steel roulette ball rolls counterclockwise inside a roulette wheel with a diameter of 30 centimeters. The ball makes 2 revolutions in 1.2 seconds. What kind of circular motion is this? This is asking about uniform circular motion, right? The ball makes 2 revolutions in 1.2 seconds. Look carefully, there's no angular acceleration, right? Then you can solve the problem just by drawing the omega t and theta t graphs. As I mentioned before, for any problem without angular acceleration, the graphs will look like this. Okay, so we're looking at the alpha t, omega t, and theta t graphs for a case with 0 angular acceleration. Since the problem doesn't mention any angular acceleration, we can just assume it's 0, right? Now let's look at omega. How do we calculate omega? Omega is the angle over time, right? Angle over time. Do you understand? So here the time is 1.2 seconds, right? So we have a time of 1.2 seconds for 2 revolutions. Since we know 1 revolution is 2 pi, 2 revolutions must be 4 pi. Simple enough, right? Let's calculate. Hold on a second. Then it comes out to be 3.33 pi. You can just convert pi to a value and multiply it. When calculated, the angular velocity is 10.47. The angular velocity of the ball is 10.47 radians per second. Or you could write it as 3.33 pi radians per second. Okay? You're managing to keep up even if it's a bit fast, right? You understand the solution method, right? So let's look here when it's 2 seconds. At 2 seconds, what happens is that the ball, when it is 2 seconds, this value is delta theta, right? Then at 2 seconds, what is the area? Since it is 10.47, this angle comes out to 20.9, right? And this is delta theta, correct? The area delta theta is base times height, right? So delta theta is 10.47 times 2 seconds. Calculating this gives us 20.9 radians. So this height on the theta t graph is 20.9 radians. This means the ball's angular position is 20.9 radians. Simple, right? It's the same as linear motion, isn't it? The only slightly difficult part, as I said, is the new notation and terminology. You are learning new notations and units, so focus on these parts a bit more and study. You need to memorize this. If I don't memorize that theta is in radians, I won't be able to solve rotation problems. Got it? This is not memorizing a formula, it's something you naturally have to know because it's about learning something new. This time, we're learning new scalar and vector concepts. All right, make sure to review. The method of solving is the same. As for centripetal acceleration or centripetal force, I will teach you those really well next time when we learn about force and acceleration. For now, if you know this much, you can solve any circular motion problem you encounter. I'll see you in the next video with some practice problems, so be sure to review everything we've covered. Thanks for watching.